And precalculus. Finally, a couple things from lesson 5. This is called sample sets of data. And this is where it gets a little bit closer to what you are usually dealing with statistics, because the power of statistics is using sample sets in order to calculate things about everything. So, for example, let's just say you have some company and they want to decide where to put the warranty, how long of a warranty to put on an item that they manufacture, so that they're 95% sure that they will only have to replace 20% of the objects. And well, they don't have the information on how long every single one of their objects will last, because it's impossible to do that and to conduct a business where you're selling objects. So they would collect sets of data where they would observe and measure how long some of their items last, and they would use that in order to extrapolate things. Okay, so 14.5, and again, sample sets of data. And one topic that comes up in this lesson is called the standard error of the mean. Standard error of the mean. So this gets into things like, well, I mean, it's basically how far how far from the population mean might the sample mean be? So it's like, all right, we don't know, we don't have measurements for everything. So we don't have mu. We don't have what the actual average is. What we have instead is an average that's based on some subset of the data that we're trying to analyze. And how good of an approximation, how much can we trust this average to be very close to the actual average? And here's the formula. It's called sigma sub x bar, and it's equal to sigma divided by the square root of n, where n is number of data points. So an example of this would be like, let's just say we we know that let's say we know that x bar. Hold on a second. I'm going to scroll up for one thing. Sorry about that. Nope. Yeah. All right. So again, x bar is a sample mean. That's what we have measured to be the average. Okay, scrolling back down. Sorry. Oh, too far. Okay, let's just say that x bar is 57.5. And let's say you got that average using a total of um, 212 data points, and that you got that the standard deviation is 21. All right, well, let's find what let's say find, oops, black, find sigma sub x bar. Find the standard error of the mean. Okay, well, sigma sub x bar is sigma, which is 21, divided by the square root of the number of data points we had, 212. And so let's see what we get. 21 divided by the square root of 212 is 1.44. So what does that tell us? That tells us that this average that we got, 57.5, should be within 1.44 of what the actual average would be if we had, what am I trying to say? If we calculated an average based on all of the possible data points. So it's like if you were doing, let's just say, I don't know what the average, what would work with my data? 57.5 around, oh, not quite 60. The average grades are for organic chemistry tests for college freshmen. Okay, 57.5. And you're trying to get this out of all of the college students in the country, but you only sampled 212 of them. And when you collected this data, you calculated a standard deviation. Technically, it should be S. Technically, it should be S, not sigma, because this is the sample standard deviation. Anyway, standard deviation of 21. So, in other words, the average scores were 21 points below or above 57.5. That's the average distance from the average that it was. And then what you get is like, you know what? For our average being 57.5, we're very, very confident that the actual average, if we had polled all of the college freshmen who took organic chemistry, that the actual average would only be 1.44 above or below what we calculated. Okay, so there's that. And then there's something that looks very, very similar to what we were doing in lesson 4, but it is using what is finding what's called the level of confidence. So, level of confidence. What we're finding here is a 1% level of confidence. I'll put LOC for short. Is that we're at 99% sure that such and such. A 5% level of confidence is we're 95% sure. The 5% level of confidence is what seems to be the most commonly used level of confidence in statistics stuff. But depending on what you're doing, whoever is hiring the statistician might want a 99% level of confidence. So this kind of thing can look like this. Let's do a sample problem here. Let's do number 25 from the textbook. Here's what we have. Number 25. And this will do it for our statistics stuff. We are told that sigma is 0.67. We are told that n equals 80. For a lot of statistics stuff, there are a variety of statistics tests that that work if you are dealing with a quote unquote relatively large data set, or at least with a sufficiently large data set. And around 30 or 35 seems to be the kind of magic number where stuff works well versus it doesn't work well. And so an n value of 80 here is pretty good. And x bar is 5.38. And here's what we want to find. We want to find the interval. Find the interval about the sample mean such that or not such that has a 5% level of confidence. In other words, we think our mean is 5.38. We want to find what range of values we'd have to go with to be 95% sure that the actual average is somewhere within that range. So we're going to use the formula that we've used before, which is x bar plus or minus z sigma. But here, instead of it just being sigma, it's sigma sub x bar. So we're going to use that value to do this calculation. And so, yeah. So we got to find sigma sub x bar and then go from there. And we need to look at what z value we're going to use because we're dealing with 95% of the data. And what you can do, so we're going to have to go back to, well, I'll tell you what, let's find sigma sub x bar first. Then I'll show you the graph what we're going to deal with. So sigma sub x bar, again, is sigma over square root of n. So sigma is 0.67 divided by square root of 80. And so what do we get here? 0.67 divided by square root of 80. We get 0.0749. Okay, now we got to find, because what do we know now? We know this. We now know this. We don't know z yet. So what we need to do is we need to find what z value corresponds to 95% of the data being above and below your value. In other words, we need to find, that's a really bad normal distribution curve, but I'll deal with it. This would be slightly right skewed. I know it's like tilting to the left, but it's slightly right skewed means that the actual, well, never mind. So we want 95% of the data here because we want a 5% level of confidence. Now, if 95% of the data is there, what percent of it is up here at this upper tail? The percent that is at this upper tail would be 2.5% because we have 2.5% there and we have 2.5% here. That makes up the other 5%. So what I'm going to do is I'm going to look at my cumulative distribution table and either look at what z value corresponds to 2.5% of the data, or I'm going to look at my going up, my positive z values table, and look at what z value corresponds to here would be 97.5. So let's maybe do that. So we're going to go to this one, and we want 0.795. No, wait, 97.5, 0.975. So 0.975 is right there. So what's my z value there? It's 1.96. 1.96. So I go back here, and I say, all right, 1.96. And guess what? It would be the same thing if I go to the value above. So if I want the 2.5%, 0.25, no, 0.025, 0.025 is, guess what? Negative 1.96. And what was it on here? It was 1.96. So that's our plus or minus 1.96. So what I'm dealing with is my average. So this is 5.38, 5.38 plus or minus 1.96 times sigma sub x bar times 0.0749. Okay. So then what does that give us? That if I do the minus first, 5.38 minus 1.96 times 0.0749, I get 5.203. And then if I add 5.38 plus 1.96 times 0.0749, I get 5.527. Okay, so based on how many data points I was dealing with, and based on what the standard deviation of those data points were, or was, then I can say with 95% certainty or a 5% level of confidence that the actual average of all of the data would be somewhere in this range between 5.203 and 5.527. All right, so that is one more little flavor of some of the stuff that can come up with statistics. We didn't get into hypothesis testing. That's one of the other big things that comes up, but this at least gets your feet wet a little bit and would help you get, I think, a very good start to a statistics course if you took one at some point in the future. All right, that wraps it up for this year. So, hope you learned some good stuff. Hope you found some stuff fascinating. Hope your eyes were open to new aspects of math. And I really hope the Chapter 15 test goes well for you.